done with respect to the repair and remanufacturing of the parts within the direct and depreciation process. And also we have done some topological optimization with respect to some aerospace brackets or some kind of the knuckle joints and other aspects and that. This is what the outline which I am going to give you a brief what work we have done, how we can able to make use of the DED with respect to the repairing aspects and what kind of components we can able to repair and what kind of components not able to repair. As you are already know the basics of IT manufacturing process. Professor David has already discussed. Here we can make it terminology as a 3D printing or IT manufacturing process. As we are going to decorate the component by layer by layer using three-dimensional CAD models. That's what you are earlier it was because he is the founder as IT manufacturing process. Earlier when we started in 1980s, making of prototypes. Now it's a direct manufacturing of any kind of a components. Directly we can able to manufacture near-nested components, or we can able to fabricate, or we can able to repair the components. That is what possible with any kind of complex components. That will reduce the time and as well as the wastage of the materials. That's what possible with your IT manufacturing process. But with respect to his thoughts, Professor thoughts, and as well with Charles Alva, with the other big team members, for the next 5 to 10 years, this IT manufacturing will be a standard manufacturing technology. Now we are not much commercialized this IT manufacturing with respect to the industry scenarios. Many of the R&Ds are still going on in this IT manufacturing process. But with respect to some static parts, you might be knowing the leaf nozzle that GA has having a patent is already going to be used with respect to the many of the industries. And that is already used and is already manufactured in all the aircraft. We are using that laser forward field manufactured leaf nozzle. And also many other static parts is also approved by the authorization of the quality and standard. Even the ASTM has approved. But with respect to even now medical, the knee implants or the hip implant has been approved to put it into the customized implant with respect to the patients. But if you take the 5 years back, it was not approved. Because we need to see how much extent it is going to be affected. Will it going to be beneficial for his life, or it's not going to be beneficial. There are several studies have been characterized and done, and even FDA has approved to put it to the patients. Even the India, many of the companies might be knowing the WTD and some other companies, Jejal Medical. They are making all our customized implants with our titanium materials. Titanium 64 is more biocompatible. Because of that, even 3167 is also used in applications where we can able to put like some kind of a screws or some kind of a plates. Especially with respect to implants, they are making use of the titanium 64, and that the grade 21 is biocompatible. And even the innovative designs is going to be enabled like a generative designs. That's what the topologically optimized designs, the generative designs based on your artificial intelligence algorithms, or which we can able to make use for our new materials. It is going to be a common when it is removed from the constraints of the traditional manufacturing process. Because that is what required. We are already fixed with the design aspects. Because we know manufacturing process steps. Because we have to make with the conventional, either casting, machining, or maybe extrusion, these kind of process. Because earlier we are not aware of this type of manufacturing process, how we can able to generate the new designing aspects with the application. But now we can able to develop our own generative designs. We can reduce a lot of material wastage, and with respect to the application orientations, we can able to develop such kind of a generative design with our topological automation. And that is only possible with our IT manufacturing. We can able to manufacture the components. And the innovative design will be a part of continuously improving the process of production efficiency and as well as optimization. Because that's what the direct manufacturing is, a direct manufacturing with advancing to the next generation of the 3D printing machines, which enables the scalable production at the very less cost. That is what the reduced cost we can able to manufacture the scalable from prototype to the application parts. And advances in these printing techniques with respect to the digital materials are driving progress in the applied manufacturing as well as in the production science and as well as the production process aspects also. But when you see these, whenever I'm talking about the generative designs, that's even the hexagon or the smooth fact or even end topology, these are the new software which are available to make some kind of a generative designs also. But earlier, if you see one example of our piston head, it was made by the extruder casting and then machine was used. But now, can we able to print such kind of a part of the manufacturing process? Will it be sustainable to use such kind of a load and as well as the temperature and other aspects which we are using for the dynamic aspects? But there we are meeting a lot of challenges. Is it possible to adopt or redo or not? Because many of our constraints in the thoughts as till more than 40 years we are running in the manufacturing process, it cannot be used for the dynamic applications. Majorly we are focusing on the static parts. But if you take this example, is definitely the dynamic part. Because there you can have a lot of fatigue loads is going to be applied on this. But one of these Mahel 3D pistons and even elemental 3D, they have developed these kind of the modified topologically optimized the piston heads, and GT91 car they have already adopted this kind of a Ferrari car, this kind of a titanium printed piston heads also. And this is giving more horsepower than the solid pistons, and as well as it is the weight reductions that will improve the efficiency of the vehicle. That's what it is mainly focusing to develop this kind of the weight reduction, high strength to weight ratio, and as a generative design components also. And this is another some kind of a brackets which we can even we are using it for some kind of a sports bikes, the KTM bikes. These kind of generative designs, this is very much required to replace with the some kind of the existing parts. That's what we can able to do. But to generate these kind of designs, we need to understand what is the initial design ideas which is represented or existing in the models, and then can we able to provide any kind of some new solution with same or maybe change with respect to the recommendations, and with that going to be evaluated to be suitable for the satisfactory with respect to the factor of safety or with other design considerations or with respect to other the loading considerations, mechanical properties. Then we need to provide some kind of a solution whether the final design solution is suitable or not. That's how we have to think to make into a selection and generative designs which we can able to develop with respect to the existing components. And if you see, when we say the optimization, even generative designs, or when we can say the topology optimizations, first it comes our structural optimizations. Like it is a design techniques that uses our numerical optimizations and as well as to create the cost effective and the material efficient models of the structures. If you see here, this is what the size optimization. The initial component is very big and then we have optimized to minimize the size, and it may be a shape optimization and it may be a topology optimization. Now we require these kind of topologically optimized component for the real-time applications. If you see some kind of a chair designs or the bench designs, earlier we have having a concept to make it to these kind of parts. That is how now we can see a lot of generative designs, optimized designs. Those are more attractive as well as easy to manufacture and as well as the minimum cost we can able to manufacture. That's what if you adopt our new advancements and technological development, then we can able to generate these kinds of attractive developments. And if you see, then coming to this topological optimization, which is a powerful optimization approach, it can able to create a innovative designs. If you see one example here, this is some kind of a bracket, structural bracket. This was we are made by the machining and as well as with welding and to make this kind of a bracket and then we have made with several holes by the drilling and but this costs almost one part is equivalent of 5,000 rupees. But can we able to change the designs and we can be able to make it very lightweight and improve its performance, which may be used in your aerospace, that may be used in your automotive aspects, or it may be used in architectural aesthetic appearance also. Yesterday the professor has showed one of the connection joints which can be used to give a more aesthetic appearances. Like that, we need to think how we can able to modify. That's what your other people and in our one of the schools. Topology is the most usually softwares and as well as another one is the example. They have tried to simulate it where the load is acting onto this modes and where the structural part is existing and with providing the several constraints and as well as material properties. And if you see, this is what the optimized raw topology optimization. But raw will be not be efficient to manufacture with respect to your ready manufacturing. We need to do some kind of smoothing to make it be a more attractive as well as a finished part which can able to use for your ready manufacturing process. That is one of the component. It will save a lot of the weight of the component and other aspects. The another one, if you see, this is what the hexagon, the collision. They have made this kind of the part by the topology optimization with the MSc software. They have started with the design and they have made with several iterations with the FEM to make which is the best optimal solutions. And how we can able to print that part, because topology optimization gives a lot of generative designs and it can able to minimize wherever the load is not and wherever the situation is not there. But will it possible to print and what orientation we have to print it? That's a major challenging issue also is going to come in our topology optimization with respect to DED. That's what they have made and they have provided a lot of support structures. And another one, if you see here, the reference finite element model, and then we need to perform the design. Then we have to do several iterations to get it to a redesign, validation, and then we have to go for the topology optimizations. That's what the key consideration is. The reference FEM is a crucial tool to compare progress in the mass production, stress factor, and as well as the factors. That is what required when we understand the topology optimization of the designs. And after if you able to make that product with the manufacturing, then you can go for the real-time component manufacturing, maybe with respect to metals or maybe with respect to the particular component what material is made of. And if you see one study with our undergraduates we have done, this is what the original component of an engine blanket. You might be seeing in your lot of publications are also there with respect to this part. Lot of topologically optimized designs also. But can it be redesigned more efficiently than the existing designs? How much extent you can able to save the materials and as well as to improve its existing performance? And I will show you this is what the existing designs from this they have published already in 2021, and this is what the optimal design they were saying. But with respect to our ideal, how we can able to redesign it more attractive manner and minimal cost, minimal wastage of the materials compared with the published or the existing components. This is what the data we have taken and we have tried to do the topological optimization with our top as well as one another software is Altair, and as well as even with the ANSYS FEM we can able to do the topology optimization. We try to compare all these kind of models with the different softwares. This is going to be a best solution for making topology optimization and as well the weight reduction. This is what the component we have finally got with our the end top and as well with the another one is the hexagon software that MSC control. We have got that final optimized rejecting bracket and we have made with our initially with the PLA polymers with the FDM process. And then finally we have printed with our DED manufacturing, the board bed feature process. This is where in this orientation we have provided very less minimum structures, minimum support structures. Because when we wanted to print orientation is very important aspects. Because it will generate a lot of heat accumulations in the part printing. That is going to create a lot of deformation during the printing. And as well as if you do not provide support structures, there may be a chance of the delaminations and it's going to peel out and even maybe going to create some kind of cracks in the printed parts. That is where we have tried to understand in which orientation is going to be the best. That's what we have created with minimal support structures. And if you see the another part, this is what the method which is used for the bachelors, they can able to go for different kinds of computations. This is what the initial knuckle, it was the existing designs. So almost the weight is model is 0.75 kg. Then this component can be able to minimize because their weight is the major constraint in such kind of a knuckle for the terrain vehicles. But they wanted to reduce the lot of the weight of the component. Then we started with how we can able to redesign it. Where and all the loads and as well as the factor of safety we have considered. And this is what we have done with the several iterations with the FEM and as well as NTOP. And finally we end up with the optimal designs of the 0.276 kg of the component. Means almost we have reduced 65% of the weight of the components. That is what it is required understanding of the topology optimizations. How much extent we can able to reduce the weight and as well as considering the safe factor of safety and other stress distribution of the mechanical properties. This is where it is very much important aspects. And other with respect to advanced simulation technologies, with respect to evaluating your DED manufacturing produced parts. That's what we need to simulate and as well as to predict and minimize the distortion defects in the part which is produced by the DED manufacturing. If you do not understand the simulation aspects, because we have to do several iterations to find out the optimum process conditions. Because we cannot able to run all the experiments with all kind of materials. Means we need to know what is the optimal process conditions which we can able to print. Even if you might be aware that if you print some kind of a cubes with the optimal conditions, that may not work for your real components. If I want to make some kind of a small bracket, if you use the optimal process condition which you have made for the cube, it's not going to work for your some kind of a bracket. What will be the challenging issues we are facing? Is it only the process conditions, or is it only the part print orientations, or it may be just to the deposition strategies? Even though you may be considering the deposition strategies for the simple cube, because it's a complete solid cube, and where you are going to give a lot of deposition strategies, hexagonal scan pattern with different linear, bidirectional, just a lot of scan patterns you can able to optimize, you can do a best density. But the scan patterns also plays another important role to distribute the residual stresses in the part. But when it comes to a brackets or some complex components, they need to think of what kind of scan patterns, strategies we have to operate to applicate the components. Because simple scan strategies may not work with respect to the complex components. That's what the major aspects is. This is where simulation enables to calculate the thermal models as well as mechanical and mechanical changes during happening in our DED manufacturing process. That simulation tool will help to verify the AM parts to meet strict quality and its performance standards. Right? They reduce the need of trial and error designs which we can able to do with your printing. Because you might be buy the machine from the 3D systems or maybe Trump or maybe the other concentrators or DM3D and all. They will give you the standardized optimal process conditions for only for a few materials. They might be giving for titanium, they might be giving for stainless steel, 74 pH, or maybe aluminum, or maybe even inconel. Because this is the major materials, the work, the research aspect has been done in these materials. But if you want to give some kind of your customized materials, if you want to make some kind of a bronze, if you want to make some kind of a gold or some other materials, the lot of research data which is not available to feed into the optimal process condition into the machine. Well, sometimes what happens, whatever the process condition they are given, which will not be suits to your materials, because we are not buying the raw materials from that manufacturers. Because we are using our own raw materials or using into our head manufacturing machines. Because the powder distribution, what kind of powder quality we are using, that's also going to be major challenging issues when we optimize the process conditions. That is where it is required. We need to understand the numerical modeling to simulate to understand how efficiently we can minimize the trial and error aspects and the design aspects. And the high fidelity of the simulations which will provide the detailed insight into the melt pool dynamics and as well as the phase transformation, which is crucial for our certified parts in the aerospace and as well as the medical industries. It's what it is required, especially in the aerospace and the medical industries and all. And the physics-based simulations, because we might be doing the FEA with the ANSYS and all. So it is very much essential to assign the quality and the conformance of our manufacturing. Because you might be knowing nowadays there are a lot of the in situ monitoring and they can able to give the feedback signals. In what way they are going to give the feedback signals, in what way they are understanding your application of the machine learning that can able to detect the multiple temperatures and as well as to adjust its laser power as well as the scan speeds. Because you might be knowing the one component if you want to manufacture your laser power, scan speed is the major important factors. That's what the process map yesterday Professor David has told you. Process map is going to get the optimal process conditions where you want to have a high mechanical properties and as well as the geometrical components with minimal defects. That process map, when we are going to develop, we need to understand a lot of application of the machine learning. But how this machine learning feedback signal is going to give into the systems to adjust your laser power as well as the scan speeds. Because once the part is going to be developed for the several height and then the heat accumulation is also going to be very high. Then we need to optimize the laser power is very important with respect to the scan speed. And if you do not optimize this scan speed and the power, then you will end up with a lot of thermally induced and as well the deformed parts in the ultimately at the end. That's why it is required to understand the physics-based simulation aspects. And simplified simulation models, especially for the powder bed fusion process, which is going to be a predefined libraries will be there, even the thermal strain data will be available in the, because nowadays for the PVF is a lot of work has been done and also numerical studies is also done. But with respect to DED, very minimal work. They are trying to adapt with our welding technologies. How we have done for the TIG welding or MIG welding, same kind of way they are trying to adapt. But when you consider with respect to the laser powered DED process, if you consider the welding process, almost 100% of the material is melting and deposition is taking place. But with respect to laser powered DED, only 40 to 60% of our powders are melting and solidification is taking place. Because how much, what about the reflectivity of the materials and what about the absorbability of the materials and how much lossage. Here the melt pool formation is different than your welding. And compared to welding, the rapid solidification takes place in the laser DED process. That is where a lot of challenges are with respect to the laser DED process and even the fully coupled thermomechanical simulations which can incorporate the scan techniques to generate the thermal profiles that drive the mechanical analysis with respect to improving the distortion, friction and accuracy and all. Even the high fidelity model that can able to simulate the complex manufacturing physics of the melt pool and as well as capturing the phases and the solidifications and as well as the microstructural evolution. Nowadays we are having very advanced numerical model you can able to understand as well as the microstructure which is going to be developed in the manufacturing components. This way we are trying to, and even the multiple machines, process and as well the materials to define our game environment today, because very long DED manufacturing has witnessed strong growth since from more than 40 years. We have a strong focus shifted from the prototype to the manufacturing of the components, the functional components. But the critical challenges is still persist in the industries, including the build repeatabilities. Because if I want to print one component today, tomorrow if I use the different powders or different machine, I am not going to get the repeatabilities, build repeatabilities, or the process scalabilities, or the stability of the DED process or the LVP process. Why we are having these challenges with respect to repeatabilities? Is it because of the process, or is it because of the raw materials, or is it because of the optimal conditions what we have set into the machine to fabricate the components? Even if you take, there are several manufacturers. Yesterday I showed DED machine manufacturers, even the India BMW manufacturing, and even the drum laser is there. If I make a component from the drum laser as well as your BMW, both we are going to get the different as well as the repeatability aspects, the components strength as well as in the other aspects. Is it because of the process, or is it because of what we have tried to understand and optimize the process conditions? Because we need to understand ultimately how much G by R ratio. That's what completely with respect to the microstructural aspects. With respect to the solidification as well as cooling rate and how much energy density we are using, as Professor has mentioned, you need to use a very high energy density which is less than the pure formations to get the better mechanical properties. Even you may using optimal energy densities to fabricate the component, but that may not going to get the higher mechanical properties. That's what we need to see the quality of powders which we are using for manufacturing and the energy density which we are using for manufacturing the part, whatever is the machines which we are using. That's what the critical issues or challenges are still existing. That's where advanced digital tools are addressing these kind of issues with like generative designs or the lattice or maybe even the hardware integrations or even maintaining the distortion as well as the shape compensations also. The AM has a greatly expanded with the multiple techniques and as well as the technologies to meet the diverse industries and as well as the material needs. Because whatever materials which we can able to make to solidify, all materials which we can able to use in our manufacturing process. There was no kind of a constraint with respect to designs or with respect to the materials. That's what we can able to meet the diverse industries as well as the materials needs. And even the indirect, that is in the direct in the deposition process, the molten material is deposited to the nozzle, either maybe on the multi-axis or maybe on the CNC machines also, with the deposition heads also. That's why we can able to deposit the components with different aspects also. Each AM process is a family of a specific raw materials. That's what maybe powders or wire or maybe the ribbons, or it may be using with respect to the different the material types, maybe plastic materials, metals, or maybe ceramics, or maybe even composites. That's how that 7 categories have been categorized. Even in the DED process, direct energy deposition process, we have several categories. That's what we can use arc, or we can use laser, or we can use as an electron beam also. But with this, all the 3 processes are suitable for kind of all applications. Where we have to choose your laser DED process, and where we have to choose your arc based DED process, and where we have to choose your electron beam manufacturing process. All the concept and the mechanism is same, except we are using a different energy sources and as well the different feedstock materials. Either the powder we are using or either the wire we are using. But one example he has shown in the Amsterdam, the bridge which is made by the wire manufacturing process. Can we able to make such kind of a very big bridge with your laser DED process, or with your even the laser wire DED process? It's not possible, because where we want to go for a very structural components, very big structural components, more than 5 feet. There we can able to use your wire manufacturing process, because there we are not much worried about geometrical aspects, geometrical accuracies. We are not much constrained. In such cases, we can use our wire cut manufacturing to make the components. But where we want to have very preciseness and the quality aspects, then we can come back to our laser diode process. If you see here, some of the component is already existing, which are maybe made by the cold bed fusion process. I want to add just additional feature under the existing components. Then I need to go with our laser DED process. One of the beam technology, that's what now they have added. They made a cold bed manufactured component with along with the additional features. If you see, these are the features which is added by the laser DED process. Means any kind of existing components we can able to repair, or we can able to add additional structural aspects, additional features. It can be possible by the laser DED process also. And if you see, how does this direct energy deposition process will work? Because I am not going to go explain this, because you are already aware that how it works and how process we can able to make it. This is what the different technology and the heat sources and what are the methods which is used in today with respect to all kind of this direct energy deposition process. And if you see, this is what with respect to some kind of implants, medical aspects. Yesterday some of you are having questions where we have to use electron beam direct energy deposition process, where we can use electron beam cold bed fusion process, because it's highly expensive, because we need to have a electron energy source and we also completely battery, because whenever the part we are going to manufacture the electron beam, definitely it's going to be very expensive, because we have to maintain the atmosphere as well as energy source what we are using. If you see such kind of a components where we can majorly use for your medical applications. And if you want to see the arc based, wire arc based, you can use for commercial applications. And if you want to make with the laser wire or with the powder DED process, these kind of a part which can be used for repairing or maybe name shape components also. But nowadays the metal has come up with lot of advancements. Even the is going to talk about in the tomorrow, the hybrid technologies. Means the metal has that capabilities to make the component as well as to machine and as well as to develop additional features under the existing components. In the same machine, they have put the CNC milling and the drilling as well as with respect to the wire-based depositions. But if you compare these two technologies with the wire, the deposition rate is low. Because even if you go with 36 kg per hour in wire or based manufacturing, but here we can go only maximum of 2 kg per hour. Almost 2 kg we can able to melt and deposit in the laser based compared with the arc based. That's why if you see, this is what the lens or maybe the RPM industries have made some kind of aerospace part with the lens with the atomic and it's most cost effective and with limited materials which we can able to fabricate it. And if you see with respect to this laser based, even in our concept laser we have done a lot of studies to fabricate the near shape components. One we have tried with this injector head. This was worn out in the some of the aerospace part. They were trying to repair it, how we can able to repair it. But initially we tried with the TIG welding process. Can we able to repair? But there we are end up with lot of geometrical difficulties, because our arc has to deposit in that controlled chamber as well as one with respect to controlled geometrical aspects. But then we have come out with the laser DED process. If you see, this is what the final finished component, and then we have developed these scan strategies, as Professor Gora has discussed you, how we can able to generate the scan strategies. We have taken the three-dimensional and the defects in the parts. If you might see here, we have given a deposition strategies in this manner to deposit this kind of a part as well as this another half section of the part. But where we are having the intersections at these junctions, there we are having a lot of defects. This is mainly because of the interpolations of your the deposition at where it is interacting from the one scan strategy with respect to the another scan strategies. Definitely at this particular locations we are having a lot of reports the defects which we have faced in the issues. To address these issues we have made several iterations to bring it back to the normal, to the effectively use our laser DED process for the applications. Different type of strategies we have adopted instead of this going for this linear strategy. We adopted different kind of scan strategies that can able to minimize these kind of defects in the downstream components. The another one, as I told, electronic manufacturing process. The SIAC has made, if you see, we can able to see the differences between this laser DED process and the electronic process. See, the quality and the finish what we are getting and surface oxidations, if you maintain argon atmosphere or to use in open atmosphere conditions. Because as this is a stainless steel we have done in open atmospheric conditions and with nitrogen as a productive gases. But if you see a lot of the satellite particles we are sitting under the surface of the part. But if you see the finish of the part which is made by the electron beam, are very good surface finish and also having a low residual stresses in this EBM process compared with the laser DED process. And also we are having a high deposition rate compared with the laser DED process. That's what we can able to use even for the suitable for the large scale components. And but only the thing is here we have to maintain the vacuum environment. Because when we have to use for the electron, should be a vacuum environment is required. That's where the cost of equipment goes very, very high. Initial cost of equipment is very, very high. And if you see the another thing is this is what I wanted to mention. The laser wire DED process, the Beltio as well as the PFW aerospace in the Germany, they have made a lot of developments with respect to the wire-based systems. Earlier it was using only the arc or using the electron beam to melt your wire-based and all. Now they have made laser wire. This is what the hybrid technology I was talking. You see, this is what the milling head they have as well as the deposition head they have. In the same process, they are using a laser wire-based DED process. And if they want to machine the component and further they want to deposit additional features onto the existing component, they can able to mill it and they can able to additionally deposit the additional features. That is what with the Beltio system having this hybrid technology system. And if you see the quality of the component, means this kind of component directly we can make use for the applications. There is no need of any kind of post process. Means this is what the one ring is there, and that ring they have added additional features on that. Means directly they can use this kind of the electron beam based or the laser wire based components for the real time application without having any post processing aspects. That's what possibilities with respect to this hybrid manufacturing. And if you see, especially when I am talking about the repairing, these are all the additional features we are adding into the components. But when I am talking about the repairing, means especially for the large components, the qualification and certification is important aspects. We can able to repair it, but will that repaired part having the same kind of mechanical properties and the quality of the existing parts? We can able to generate the data with your 3D scan, and we can able to give the part plan how we can able to fabricate it up. But are we getting the same mechanical properties or better mechanical properties than the original part? That is where the challenges will come. To address these things, what we have to understand, what we have to do lot of experimentations. Means that's what we have tried to attempt one of the aspects is the rail components or the oil and gas industries components, or maybe some kind of the tooling industries components where the tooth has broken. Means this is where we can use the DED process very cost effective to qualify the components for the repairing aspects also. But for these aspects, we need to understand what are the supporting technologies which are existing. Means if you see the tool-clad cam tool for strategies, or maybe even touch pro with respect to your CMM, or maybe the thermal controls. Means during the depositions, can be able to control the temperature, and if you are able to provide some kind of a coil system to maintain the temperature during the depositions. And these are some case studies we have attempted. If you see, the one drawback is one of the gas turbine casing and all, they made the holes in a different diameters what it is required actually. That's what made by the machining and all, but it is with the nickel based supervisor and all. But how we can able to repair it? Either we have to throw the part or we have to manufacture once again, or we have to repair it. But the repairing is only possible by our laser DED process. But again, challenge is repair of incorrectly machined holes on the outer circumferences to avoid some kind of scrapping of the parts. Means we have added the solution to deposit the 30 by 30 mm of the patches in the entire part. Then again we have to delete the required dimension of the diameter. That's how we have taken the data and then we have repaired it. And another case study is if you see some of the forging molds, because in the forging industries, molds are keep on worn because they are going to give new kind of molds. Because once certain life of the component of the molds are worn out, then they have to throw it and they have to use the new molds. But here, can we able to repair such kind of molds? You see the worn out part of the mold here. This is the hard forging process. And this is what the, after the part has taken, we have done the machining, complete machining was done to make it to remove the such kind of unnecessary the worn out parts and all. And then we have tried to generate the data how much scanning which we can able to get from the worn out mold and all. And then we have tried to understand how much extent the material has worn out on the molds and all. And then we have tried to reproduce, and then we have measured with your CMM. The complete entire section is also milled, and then we have added additional materials with our DED process, and then we have finally finished with your milling process to get the repairing of this mold. And this mold has successfully used for another the making of 10,000 of components of the forging parts. That is where repairing is very much beneficial with your laser DED process. But with the other kind of technologies, repairing of these parts are very challenging and we have to throw it away. And apart from this repairing, even we can use for the laser cladding. If some part is worn out, or if I want to improve its performance, or if I want to improve its corrosion properties by hard facing, I can able to add additional corrosion resistance materials, or to improve its wear resistance materials. That's what we can able to add by our laser cladding. With the same laser direct deposition process, but we can able to add with the additional materials to improve its performance. But the main advantage is you see we can able to maintain the geometry which is in a critical and heat sensitive components, and to avoid our secondary process. Some kind of additional process we can able to minimize it. And as that we can able to reduce the grinding requirements and the overall finishing parts. Complete overall cost of manufacturing we can able to minimize, and we can able to achieve the high quality of materials properties with less than 1% dilutions. That's what possible is for laser DED cladding and other repairing aspects. And even it can ensure that the minimal heat affected zone is possible with the laser DED. Even we might be having some thoughts, can we able to repair even with the welding? The TIG welding process we can able to repair it if it is a part is very big part is worn out. Yes, we can able to repair it, but the heat affected zone and the thermal distortions are more in the TIG welding process. There we can having a lot of difficulties in the mechanical properties of the repair parts. That is where we can able to use our laser DED process. Even the small internal diameters of less than 1.5 inch we can able to repair with the laser DED process. That's what possible with the DED process. And if you see, these are all the components they are made by the repairing with the conventional methods or with the laser DED process. These are the methods and as well as some of the advantage compared with the other kind of welding technologies. And even we can try to use for the hard facing, because earlier we are trying to do some kind of heat treatments of the valve stems of some of the turbine and steam turbine shafts. But the steam turbine shafts which is going to be warm out, but how we can able to repair it? But that repairing is possible with the laser direct evacuation process. Means the challenging is depositing a hard facing material on that stems. It is a very challenging issue. There we can use the DED process, the tribal cracks and steel, because it is going to create a lot of cracks when it is going to expose to a high temperature when this melting and solidification is taking place. That is very difficult to weld. But if you maintain a temperature of preheating temperature of that the steam, the turbine shaft up to 550 degrees centigrade, then we can easily deposit the laser DED process the 10% of nickel, which will enable the crack-free processing. That can improve its life of the components, and we can also produce a new crack-free repairing techniques with our laser DED process also. That's what hard facing is very much useful in aspects of erosion, corrosion, or maybe even cavitation, and even the hard facing aspects. That's what people have done with one of the components with the laser DED process. Laser wire DED process, they have developed the satellite chips on the laser cladding of the shaft, and they have made, after laser cladding they have machined it, and then they evaluated any kind of defects after cladding which is existing in that component or not. That's what they made with the dye penetrating testing to evaluate what kind of the quality which we are getting by the laser cladding process. Means this is a high quality of satellites over the surface of this disc they have done, and they got a very good quality components. I just want to run that video. If you see another components, another case nowadays major challenging is the Pelton turbine brackets. The RAM lab has recently made an attempt to repair such kind of parts, because lot of the erosion is going to take place in this kind of the Pelton brackets. But repairing of this part was not at all made in a real case. But now we can able to repair these kind of parts by our laser wire process. They are made to address the issues. This is what the worn out area. They have taken this kind of a Pelton bracket surface area with the 3D scanners, and they have tried to understand how extensively worn out has been taken place, and what is the volume, and what kind of departure strategies we have to use for fabrication of repairing of these parts. Because Dr. Gora told you can take the data, but when you try to repair it, it's going to be challenging. Because how your scan path of a deposition strategies has to be deposited. Even during that, it may be going to create some kind of defects also. But that is where they have made a lot of attempt to address, and this can be repaired in 3 hours within 28 minutes of your arc time. That's what very minimal cost they have repaired. This is what the repair component. That's how we can able to take the data and we can able to repair it. And if you see, this is another component. They have made the scanning along with the depositions and all. If you see here, however the scanning data will work, and as well as the repairing data in the same robotic arm of your laser DED process also. If you see, this is what the 3D scanner they are attached with your robotic welding. That's what with the laser DED process. The lambda, it is going to take the entire 3D data of the scanning of the 3-dimensional data, and then immediately it will encode it to how much the worn surface area, where and how material we have to fill, and then we can able to deposit it in the same machines the additional layer of the material which you can able to add it. That's how they have made lab with new kind of developments in the same systems. But now we are having in our other systems is we are taking a data, we are processing additionally, and then we are developing a path planning, and then we are going to rebuild or develop additional materials. But that is what the advanced technological development they have made with in the same systems. They can able to capture the data and they can able to repair the data. But another aspect, if you see the repair with respect to the new make, is it going to be beneficial when you consider the repairing of the existing component? What is the cost of repairing, or what is the cost if you want to make the new component? If you see here this gas turbine maintenance requirements, because the gas turbine maintenance requirement is very high. It is dependent on the independent counts of the start hours and as well as the what kind of methods the UH has maintained. And the first stage of the nozzle, we have preventive maintenance of the repairs with respect to the replacement economics. If you see how much the nozzle has been worn out after this gas turbines and all, means if you reduce the 10% weight reduction from 10 parts to 1 part, or if you improve the efficiency of 30%, or if you make some kind of a unit reduction by 75%, or maybe you are improving some kind of a durability of that product also. That's why it is required whether we have to go for complete replacement of the part or you want to repair the existing part. Repair will continue until the part cannot be restored. That's what the minimum acceptance standards or the repair cost exceeds the replacement of the cost, then only we have to go for the complete replacement of the new part manufacturing. And the other thing is, if you see, this is one of the aerospace they have made with GE and the pattern with me. The Srinivasan has been worked on this one of the materials. These kind of additional features they wanted to add. If you see, this is the worn out part here and as well as here. You can see this is the leading edge damage on this your aircraft FSX. So, core and cobalt allied on the gas turbine unit. But the repairing of this part is even with your laser DED process is very challenging. Because when you see this kind of part is casted and machined, the microstructure of that part is equiaxed. But when we deploy these kind of additional features onto the existing part, we are going to end up with some kind of the columnar dendritic structures in that. But the mechanical properties are not going to match. Then again the part is going to be worn very quickly even if you repair it. Then what kind of solutions we have to provide? Then they have made some kind of a DFT nozzle joint with columnar dendritic. If you see, we can able to differentiate this for the existing nozzle with dendritic structures, porous dendritic. And then at the interface, what kind of the grain pool is taken place and how we can able to break that columnar grain pool. This is what we have to address to maintain the same kind of properties in the fabrication of the component. If it does not maintain the same kind of the mechanical properties or the microstructural aspects, then even the repairing does not make any sense in the repairing of the components. And if you see the other part is they have made the stick spirals. If the nozzles in the oil and gas industry they are using, this stick spirals has worn out and all, but how we can able to repair it? Because it's very hard. You can see that hardness is 278. It's very hard and all, but these ash alloy they are made with additional depositions, and even you can able to change the geometry of that spirals also. That's what they have made. If you taken the data of that three-dimensional, how much the wear has been taken place, almost 70 micron or 100 micron wear has been taken place on the spirals and then they have tried to attack with the different kind of the lots, whether we can go with the lot 1 or lot 2 or lot 3 or lot 4, which is the best we can able to repair such kind of the spirals with the addition of the materials which we can be able to repair with efficiency. That's what with the lot 4 they have made a very efficient repairing of that spirals. Even that will qualify for the DFT productions and with the modified design spirals with the examination of that raised joints, which is going to be okay with improved NOx emission and all. And even with cost saving via the scrap elimination, comparing if you want to scrap these kind of spirals and all, that is going to be a repairing is a very best advantage comparing with this scrapping of these kind of parts also. Even you can provide some kind of a new alternatives for these kind of the turbine designs also. That is also possible by the addition of this designs with respect to the existing components. Another part we have tried to make repair is this kind of the defective turbine blades. But if you see, this is what the chopped out of this defective turbine blade. We have taken the data of this chopped turbine blade, and this is the only part we wanted to add onto this bottom part. But when we taken the data, we have taken entire data of this part, complete data of the part. When we are having the original design of the part, and then we have subtracted how much the part has been defective in the blade. Then for only that much of part, we have tried to develop a scan strategies or the deposition strategies. But for the existing direct part, we cannot able to repair it, because we need to provide some kind of the machining, the milling we have done to make it easily we can able to deposit the addition of the materials. Because if you see, the surface is not completely regular. The surface is having some kind of a projection, some kind of a non-regular planes and also that kind of place we have made milling and all. Then this kind of the deposition strategies we have provided, then we have ultimately repaired with a good quality of the components also. That's what we have made with this kind of a turbine blades. The another blist, if you see here, is what one of the blist which is worn, that also we can able to repair it. And if you see, the another part is the case flange. The flange does not have some kind of a additional aspect that can also be added with additional features with this kind of a part. And if you want to make some kind of a multi-materials mold dies also. If you see, this is another case study with the laser powder DED process also. If you see, this is what the initial part which is worn, and this is what is the final part. And even this kind of a part which we can able, this is the deposit, and after that we have done the machining to get it to the original shape of the components. And major another challenges we address with the crankshaft, because crankshaft is normally going to be worn out. Because you might be knowing after 10,000 the run this crankshaft is going to go on. But how we can able to repair that complete data we have taken, how much it is worn out with the 3D scanners, and then we have tried to add some kind of the margin steels and as well as the chromium magnetic steels, and then we have deposited to get the repairing of the crankshaft. And so we have tried to make with applications of laser DED process for the repairing applications. And if you see, the another aspect is the bottom is copper and the top is some kind of a tool steel material is deposited. That's what the 400 meter is deposited on the top. This is what it is required, because when you use for the dye industries applications, we need to provide a lot of cooling. Otherwise, dye damage is going to be take place. Because if you provide a copper material, it is having a high amount of the thermal temperature resistance. Because it will dissipate very heat very quickly compared with the other materials. But here we are in the top surface, we need to have a very high hard materials which is having a high strength also. But the deposition of these two metals is going to be challenging, because at the interface we will end up with a lot of portion of thermal expansion, and the defects are going to become, even maybe deformation is going to take place. But for those aspects, we have added an internal layer. That's what the monel component is used between these two components for this molding part. That is going to be acts as a buffer layer between the tool steel and as well the base part. That is going to give a improvement in this the functional grade mold, which can improve the efficiency 30% and as well as 80%. That is where it is required for repairing of the molds and all. And with respect to all these things, as I told, whether the repaired part will have the same kind of mechanical properties or not, how do we have to qualify? Yes, we have done the repairing. Is it having the same mechanical properties with respect to the substrate? But that is what we have done initial preliminary studies with respect to some of the titanium alloys. We have taken the data of the surface deposition strategies and as well how what kind of surface finish we are having, and what kind of microstructure we are getting. Initially tested coupons we have printed, some kind of a 10 mm by 10 mm or maybe 50 by 50 mm coupons we have printed. And we have measured what is the melt pool at different locations of the entire fabricated components. What is the axe spacing, what is the columnar structures, as well as the size of the structures, grain sizes and all. And we have tried to analyze with wrought materials mechanical properties, as well as the only deposited material mechanical properties, with the different orientation you see in the build direction as well as in the across the build direction. And that's what if you see, this is what with respect to horizontal, the vertical depositions and the 45-degree inclinations, and this is what with the half section of the repair and the rod line, and one cross section and another with the two cross sections. And we have compared all the mechanical properties with respect to strength, hardness, as well as the elongation, even the heat, fatigue properties also we have tested. Because ultimately, once you understand all this data, then only you can able to use it for the repairing applications. Otherwise, it is end up with a different mechanical properties, or even if it is repaired, it may not be useful for application. That's what if you see the strength is matching with the rod materials, except the elongation, the strength as well as the tensile strength and ultimate strength is matching with your rod materials. But only the elongation is not matching because we are having a lot of the porosity defects. But these porosity defects, even the optimal conditions you are using, which we cannot able to minimize. Because in additive manufacturing, porosity is a common aspect, but you can be minimized means we have to go for the hipping. After this deposited component, if you heap it, we can try to improve its elongation properties, but not as extent of the rotalize. We can try to match near to the rotalize, not it can be completely same as the rotalize. But that is why by the heaping process we can able to minimize it. And also we have tested, that's what I told, the fatigue properties and the crack propagation properties also. You will see that fatigue properties in all the conditions with respect to rotalize, even in the crack propagation which is matching, then we have tried to address how we can able to repair that some of the real component. And repairing is also challenging because the data which we have taken, the CT scan data of that existing component could not able to repair it. We could not able to generate the scan strategies for the component. Then we have made additional milling to create our own defects in the defected part also. This is what we have built it, and then we have taken the data, and then we have tried to generate the data for our build defective data, and then we have repaired by the laser drilling process. That is how we have made to repair the term of the automotive titanium components also. This is what to qualify all the things we need to understand that after mechanical properties, microstructural, then we have to go for repairing application. That way we can majorly use for our laser reading process also. With respect to another some of the things I wanted to just show you quickly. With respect to VAM process, we have made several studies and you see quickly I will go through this. I will not come to this. These are some of the big parts it is made by the VAM process. And if you see one of the die designs, they have made with VAM. But if you compare this VAM process with your DED process, laser power DED process, which is going to be more beneficial when you want to repair the dies and all. This is the laser power DED process is more beneficial, or laser wire DED, or maybe arc DED process is beneficial.
You have to compare the efficiency or the
in terms of the quality, because especially in the die industry, we need to
why DD?
powder LED.
See, lasers is both we can use for the wire as well as for the powder. But when you go with the powder, its complete repairing of that part is difficult, and as well as it's going to be a more expensive compared with your wire art based manufacturing process or with laser based wire DED process. But if you compare with only with wire arc as well as the laser wire DED process, laser wire DED process is going to be a good mechanical properties and having a good quality of components, and even the post machining is minimum. But if you use your wire arc manufacturing process, it is a cost effective process, but additionally it will add up post machining aspects. That's what we have tried to attempt making such kind of a dies and all. Okay. And another thing, I will not show these things Professor already showed. If you see, the another thing is we can able to make bimetallic components. In BDF, making a bimetallic components is highly challenging. It's very difficult because we have to mix the powders, or we have to end up with the scrap of the powder particles. But in DED, without losing the powder materials, we can feed n number of materials when we are having a more number of feedstock materials of the hoppers and all. In the same material, we can able to provide bimetallic or even the functional grade materials. We can feed into the nozzle, coaxial nozzle, if you are having a multiple hoppers. You can one hopper you can feed the titanium, one hopper you can feed the copper, in another hopper you can feed the aluminum. You can combine, you can able to fabricate the grade structures or even the bimetallic structures also. And another component is, if you see, this is what the fabricated components with your wire are, but ultimately you need to go with this is the machine components. For one such kind of applications, we have worked for the stereo aerospace when I was doing my postdoctoral things and all. This is what the big robotic system with wire arc manufacturing we have used. This is one of the big ship propeller is manufactured with marine steel materials. And another one is we have made with this is what the major component which was already tried to implement into the aircraft brackets. The door which was made by earlier the fastening and as well as the sheet metals and all. They are using lot of the spot welding and as well as the fastening aspects. If you see the right hand side, this is what the aircraft door bracket will be. But they want to minimize the weight of the reduction. They want to reduce lot of the weight, can able to improve the efficiency. And also need to have the same quality of the strength. But we have started with manufacturing with your wire arc manufacturing process. This is what the component we have made. Even if you see lot of the delaminations and deformations are existing. This is what we have taken the plain sheet and we have made try to manufacture the different kind of the walls and all. But even at the junctions, you can able to see a lot of defects are existing. But we have addressed all these issues after several attempts by considering different path planning strategies and what kind of axis, whether we are using 3 axis, whether we are going with 5 axis, and how the scanning or deposition strategy. If you see, even after machining, you can able to see a lot of cracks. This is what the deposited components with these kind of deposition strategies, but we are end up with the defects. But with all these kind of understandings, we have made the efficient defect-free component for that kind of a stereo aerospace and all. And if you see, this is what the final component we have made. If you see, this is what the final component we have made. Means we have addressed how we can able to fix our plate without having any kind of deformations. Means that will minimize the residual stresses and have the heat accumulation. But for these, we need to change our path planning. Earlier, what we have gone for the linear path planning is not suitable for this kind of components. Then we have tried to address the non-linear path planning. Then we have made it. There is no delaminations which are occurred during the plate or the deposited things. For this, we have also made several holes to distribute the heat accumulation in the parts also. What I try to say. And another aspects also, we have made some kind of a ducts. If you see with the 3 axis, what defect we are facing because of the 3 axis tool paths. And if you go with the 5 axis tool paths, so you can able to efficiently fabricate this kind of attacks also. That's what if you understand this the CAD bed models with the different kind of slice based neutral axis with respect to the closed axis, you can able to fabricate the efficient components also. The several understandings which we have also made with the different studies. It's what just with respect to the wire-based archaic manufacturing process. Okay. Thank you. I will end up with this talk. Afternoon 2 o'clock we will start. Okay. If you have any queries, then directly ask me. I will can discuss with you last time. Okay. If there are no queries, quickly go for the lunch. 2 o'clock immediately we start for the another session for the remanufacturing design as well as. Thank you.